So we're in section 4.7 today. And we're going to come up with inverse trig functions. We want to work with inverse trig functions. So let's start off by remembering a little bit about inverse functions in general. So if we're looking at a graph of a function, we'll talk about graphs since we've been doing a lot of graphs. If we're looking at a graph of a function, or a graph of some kind of relationship, how do we know if that graph represents a function? Vertical line test. So that tells us if it's a function. How do we tell, looking at the graph, if our function has an inverse? Horizontal line test. So to have an inverse, our graph has to pass the horizontal line test. Now before we start talking about these trig functions, what's special about inverse functions? Why would we want to find one? What's special about the relationship between a function and its inverse? Let me write a function down. X squared. If we have an x squared, what's the inverse function of x squared? Square root of x. So what's special about these two functions and how they relate to each other? So they reflect over the line y equals x, right? Our graph. What do they do to each other? Yeah, Sam says they cancel each other out, essentially. So we often say they undo each other. So that's one reason that we want to look at an inverse trig functions. We want functions that will undo the trig function. How do we undo a trig function? So thinking of these things, let me grab a picture of a graph of our sine function. Oops. That's not what I wanted to do. I need to go here. There we go. And we're hopefully relatively familiar with what this graph looks like now. We've been working with it for a fair amount of time. All right, so there's a little bit of our graph of our sine function. Does this graph pass the horizontal line test? No. It does not. So the way we have this graph, our function wouldn't pass the horizontal line test. We couldn't find an inverse. So what we have to do is we have to restrict the domain of our sine function. So our sine function, what is the range of the sine function? -1 to 1, right? So I want to get a piece of the function that includes that entire range. So I'm going to take this piece of the graph from here to here, right along here. I'm going to go, and I'm going to take that piece of the graph. If we're looking at just that piece of the graph of the sine function, would that pass the horizontal line test? Yes. That piece of the function also contains the entire range of the sine function from -1 to 1. This point on our graph, on our axis, this is negative pi over 2, and this is positive pi over 2. So to define an inverse function for the sine function, we're going to restrict the domain negative pi over 2 to pi over 2. And then if I'm looking at just that piece of the sine function, I can define an inverse sine function. So then we can write that our inverse sine function, so we say our inverse sine function y equals, and we write it a couple of ways. So inverse sine, or y equals arc sine x. And we can think of this as an angle. So our inverse sine function is going to be an angle. Our output is going to be an angle. So this is the angle whose sine is x. That's the way we can think about this. So we put in a number into our inverse sine function, and we get out an angle. Now the tricky thing is, because we restricted the domain of our sine function, when we are in for inverse functions, the domain becomes the range. So the range of our inverse function is minus pi over 2 to pi over 2. So this is the angle whose sine is x between minus pi over 2 to pi over 2. So our output of our inverse sine function is always between negative pi over 2 and positive pi over 2. So if we look at our unit circle, we're looking for angles on this half of the circle, and down here in the fourth quadrant, we're saying our angles are negative. So if I went around here, for example, 7 pi over 4 is not between negative pi over 2 and pi over 2. 7 pi over 4 is way bigger than pi over 2. So this, rather than being 7 pi over 4, would be negative pi over 4. So we're looking at our positive angles here and our negative angles here, so that we can have an inverse function for our sine function. That's our restriction for our inverse function. That's where most of the mistakes get made with inverse trig functions, is not paying attention to our domain restriction of our original function. So this is the angle whose sine is x, and we're looking between negative pi over 2, pi over 2. Let me grab a picture of the graph of the inverse sine function, and I'll put it in right here. Is that number 4? Yes. So here's a graph of our inverse sine function. I can plug in any number. My domain of the inverse sine function is from negative 1 to 1. There's no angle whose sine is larger than 1 or less than negative 1. So our sines are always between negative 1 and 1. There's no angle whose sine is larger than 1 or smaller than negative 1. And our range is negative pi over 2 to pi over 2. And we can think of this as a piece of the sine function reflected over the line y equals x. So this is our 0, and you go up to the maximum. So let's practice a little bit with this idea of this inverse sine function. So let's say we want to look at the inverse sine of negative 1. And the way we're thinking of this is the angle whose sine is negative 1. And we're between negative pi over 2 and pi over 2. So what angle between negative pi over 2 and pi over 2 gives us a sine of negative 1? A y coordinates on our unit circle of negative 1. What is it? Negative pi halves. So our angle, theta, equals negative pi over 2 because the sine of negative pi over 2 is negative 1. So often students are going to want to say, oh, it's 3 pi over 2. The sine of 3 pi over 2 is negative 1. Well, 3 pi over 2 is way larger than pi over 2. So that's outside of the domain restriction of our original function. Positive angles here, negative angles there. How about the inverse sine? I'll write it the other way. Arcsine of 1/2. So this is the angle. Whose sine is 1/2. So what angle is going to give me a sine of 1/2? What was it? Pi over 6. So theta equals pi over 6 because the sine of pi over 6 equals 1/2. And pi over 6 is between pi over 2 and negative pi over 2. All right, ladies, computers. Let's look at one more, and then we'll talk about our other inverse trig functions. How about the inverse sine of square root of 3? So we're asking what angle gives us a sine of square root of 3? Pi over 3. So let's back up a little bit here before we decide on an answer. How big is square root of 3? What's square root of 3 approximately? 1.72 something, 1.7. What angle has a sine of 1.7? What's the range of our sine function? -1 to 1. Is there any angle that has a sine bigger than 1? No. This does not exist. Remember, our domain for our inverse sine function is between -1 and 1. So if I plug in a number that's larger than +1 or smaller than -1, I get something that doesn't exist. No angle has a sine of 1.7. So this is no solution. So that was a trick question. All right. So the important things about inverse sine function. Inverse sine function gives us an angle. Our angle is always between negative pi over 2 and pi over 2. And our domain of our inverse function has to be between -1 and 1. I think it's something that is the sine of some angle. All right, questions on this so far? Yes?
So
always in the first or fourth quadrant, and the fourth quadrant angles we're always thinking of as negative angles. Yes. All right, so let's look at the graphs of our other cosine function and tangent function, and we'll talk about how we restrict the domains of those two to come up with an inverse function. We're going to go through the same procedure for cosine. There's my cosine function, and I'll grab a graph of the tangent function. So there's a cosine function and a tangent function. I'm going to switch that one down a little bit. So for the cosine function, we're going to go through the same procedure. We want it to pass the horizontal line test. We want all of our possible domain values for cosine of x to be in that part that we take out. So what we're going to do is restrict our domain for the cosine function from here to here. So we're looking at this piece of our graph. We get all of our values between positive 1 and negative 1. So our domain restriction for cosine x, so it will have an inverse, is 0 to pi. And for the tangent x, what I'm going to do is just get rid of everything over here and get rid of everything over here. So we're just going to go from this asymptote to this asymptote. And we get all of our possible values for tangent. And our domain, we're restricting our domain, is negative pi over 2 to positive pi over 2. And then if we cut out all the rest of this part of the graph, then that graph's going to pass the horizontal line test, and we can define an inverse function. The range is, the range would be minus infinity to positive infinity, and then that becomes the domain of our inverse tangent, because the domain and the range switch for our inverse function. Yeah, good observation. All right, so our cosine function, we're going to say y equals inverse cosine of x. And this is the angle whose cosine is x. Angle between 0 and pi. Whose cosine is x. And for this one we say y equals inverse tangent of x, and I can also use the arc cosine and the arc tangent here. And this is the angle whose tangent is x, and our angle between negative pi over 2 and pi over 2. So cosine x is the oddball. Sine and tangent have our domain restrictions between negative pi over 2 and pi over 2. Cosine is from 0 to pi. So for the cosine function, we're looking for our angles here in the top half of the unit circle. For the sine and cosine, we're looking over here, and our fourth quadrant angles are negative. So let's make what I'm just going to write a couple of things, make this a little more formal, and kind of write everything in a list so we have it all together. And then we're going to practice with these inverse trig functions a little bit. And our entire homework assignment tonight is just practicing finding these inverse trig functions. So any questions on why we restrict the domain the way we do, and how we come up with these inverse functions? Okay, so we're going to say that for our inverse functions, y equals inverse sine of x if and only if sine y equals x. And the domain of my inverse function is negative 1 to 1, and the range, what I get out of my inverse function, is negative pi over 2 to pi over 2. So I can only put, this only makes sense for x equals negative 1 to 1, and I only get out an angle between pi over 2 and negative pi over 2 and pi over 2. Y equals inverse cosine of x if and only if cosine y equals x. And our domain is negative 1 to 1. There's no angle whose cosine is larger than, in absolute value, than 1. And our range for the inverse cosine is 0 to pi. So I always get an angle out between 0 and pi. And then we're going to say y equals inverse tangent of x. Again, if and only if tangent y equals x. Our domain, like Miriam pointed out, our domain is going to be negative infinity to infinity, and our range is going to be negative pi over 2 to pi over 2. So I can plug in any real number into our inverse tangent function, and I get out an angle between negative pi over 2 and pi over 2. And let me stick the graphs of the inverse cosine function, inverse tangent function down here, just so we have a visual of what we're talking about. There's my inverse cosine. So my domain of my inverse cosine function, negative 1 to 1. My range, 0 to pi. And we can think of this as the graph of cosine x reflected over the line y equals x. So here we're starting at 1, and we're going down here. So, and then my inverse tangent function. Push that down a little bit. So there's a graph of my inverse tangent function. My domain of the inverse function, any real number. And the range between negative pi over 2 and pi over 2. So our vertical asymptotes on our original function become horizontal asymptotes for the inverse tangent. So there's a picture of what our inverse functions look like. All right, so let's do a little practice with these. Oh, one other important thing with inverse trig functions, we're always dealing in radians. So when we're dealing with inverse trig functions, we're always in radians. So let's practice on a few of these. We want to find the inverse cosine of square root of 3 over 2. So this is the angle. Is angle whose cosine is square root of 3 over 2. So what angle between 0 and pi gives us a cosine of square root of 3 over 2? Pi 6. So I'm going to say theta equals pi 6 because the cosine of pi over 6 equals square root of 3 over 2. So hopefully we also see that inverse trig functions are really asking us to be familiar with the unit circle. We're kind of going both directions with our unit circle. How about the inverse tangent of 1? What angle gives us a tangent of 1?
45.
45 in radians?
Pi over 4.
Pi over 4. Yes. Because the tangent of pi over 4 equals 1. Now what if the question were tangent, inverse tangent of negative 1? What would my answer be? Negative pi over 4. Because I want my angle to be between negative pi over 2 and pi over 2. So rather than going all the way around to 3 pi over 4, or not 3 pi over, 7 pi over 4, I'm going down to the fourth quadrant as a negative angle. Let's see, how about our cosine of negative 0.5. So we want the angle whose cosine is negative 1/2. So remember our domain restriction on our cosine function was 0 to pi. So the fact that we're getting a negative here, what quadrant does that put us in if we're looking from 0 to pi? Quadrant 2. Cosine is our x coordinate, so I have a negative x coordinate, and our angle is from 0 to pi, so this is quadrant 2. So we come up with 2 pi over 3. Because the cosine of 2 pi over 3 equals negative 1/2. Let's look at one more, a little trickier this time, the arctangent of square root of 3 over 3. What angle gives us a tangent of square root of 3 over 3? Well, takes a little more work to figure out. Well, so thinking about our angles, because we have the square root of 3 involved, what does that tell us? What hint does that give us about our angles? It's got to be either 30 degrees or 60 degrees, right? Pi over 3 or pi over 6. Those are the only two angles that give us a square root of 3 somehow. And we need the sine over the cosine, the y over the x, to give us square root of 3 over 3. So is it going to be pi over 3? First of all, is it first quadrant or is it a negative angle in the fourth quadrant? It's first because it's positive. So we're in the first quadrant. So we've narrowed it down to pi over 3 or pi over 6 because those are the only two that give us a square root of 3. So which one is going to give us a sine over the cosine of square root of 3 over 2? Pi over 6. Because let's go through this. The sine of pi over 6 is 1/2. The cosine of pi over 6 is square root of 3 over 2. So the sine divided by the cosine is 1/2 divided by the square root of 3 over 2. Flip the fraction and multiply, so I get 1 over the square root of 3, which is square root of 3 over 3. So the tangent of pi over 6 is square root of 3 over 3. Tangents, the reciprocal functions are sometimes a little trickier to figure out. All right, questions on this? Our entire homework assignment tonight is just practicing with this idea. of how do we find these inverse functions. Remember, the important things to remember, our inverse functions are angles. We're talking about angles, sine and tangent. This half of the unit circle, fourth quadrant angles are negative. Cosine is the top half of the unit circle. Okay. Homework. Oh, one other thing. Some of these problems in your homework ask you to find the inverse trig functions in your calculator. Just make sure your calculator is set to radian mode. And then you just use the sine minus 1, cosine minus 1, tangent minus 1. There you go. 20 through 32 even, I think, are the calculator problems.